Welcome everyone, and many thanks for attending this first webinar of the DECAGONE project. So as a reminder, this webinar will be recorded, and all videos of the participants and mics, videos will be shut off and mics will be muted. And we will, if you have any questions, we will address all the questions in the Q&A session at the end of all presentations. Okay, so we will gather all the questions and address them at the end. So the title of the webinar is Boosting the Conversion of Industrial Waste Heat into Carbon-Free Electricity, first overview of ORC key innovations. So the agenda for today, so we have this short welcome and introduction. Then Aldo Serafino, Director of R&D Projects at Enertime in France, will present the DECAGONE project for about 15 minutes. Then we will have Trond Andresen from SINTEF Energy Research in Norway. He's a senior research scientist, and we will talk about novel waste heat recovery concepts for ORC for about 20 minutes. Then we have Christopher Schifflechner from Technical University of Munich, the chair of energy systems. He will talk about innovative waste heat to power cycle design for about 10 minutes. Then we will have Vincent Lemort, professor at University of Liège in Belgium, who will talk about ORC of design optimization, controllers, online performance measurements, and charge optimization. And then the final speaker will be Ole Martola from SpinDrive, Director of Business Development, and he will talk about maintenance-free bearings for harsh conditions for about 10 minutes. When all these presentations are done, we will address all questions in the Q&A session, and we will end this meeting with a wrap-up and conclusion. So now I will leave the floor to Aldo Serafino for the first presentation. Thank you. Your mic is muted, Aldo.
Thank you, Edouard, and good morning, everyone. I'm Aldo Serafino, Director of R&D Projects at Enertime, which is a French SME created in 2008 and based in Great Paris region with 70 employees. We manufacture turbine and compressor, and we are a producer of organic cranking cycle, high temperature heat pump, and gas expander. My role here today is introducing you to the DECAGONE projects. So I would like to start with this slide entitled Energy Efficiency and Necessity. If we have a look to this chart over there, we see that it depicts the world as a system in continuous evolution. In 2020, world population was about 7.8 billion people. And according to estimation by the International Energy Agency, in the period 2020-2050, this global population will increase by almost 2 billion, reaching in 2050 about 10 billion people. Nearly all the population increase is in emerging markets and developing economies. This trend, on the one hand, results in an increase of total energy demand. On the other hand, if no action are taken, it results in a surge in greenhouse gas emission. To indicate needed action to avoid the surging in greenhouse gas emissions, the International Energy Agency has introduced multiple scenarios in their World Energy Outlook that they publish every year. These different scenarios are indicated with different acronyms that you can see here. I will focus here on the last one that you see here below, the NZE, which is an acronym that stands for Net Zero Emission. This is the scenario envisaging zero net greenhouse gas emission by 2050. So far, we know that this is the only scenario among all these scenarios that we see here that limit the temperature increase to 1.5 Celsius degree by 2050. Now, this scenario showed that the global energy-related and industrial process emission of CO2 equivalent in 2020 is about 32 gigaton. And in 2030, it should, let's say, reduce to 21 around, and we should reach 0 by 2050. Achieving this rapid reduction in just 30 years of the CO2 emissions require a broad range of approach and technologies. The key pillar of decarbonization for the global energy system are here listed as energy efficiency, behavioral changes, electrification, renewable, hydrogen, bioenergy, and CCUS. In particular, energy efficiency and renewable are the key driver for emission reduction by 2030, and they are later on complemented by electrification, CCUS, and hydrogen in the second stage of this sprint towards 2050. Now, talking about energy efficiency, we cannot forget that industry accounts for almost 40% of the global energy consumption. In this map that is taken from the SE Energy project, we can see the relevant industrial sites with an important and elevate excess heat. The industries, let's say, each dot are the color of the dots are, let's say, used to differentiate the sector of industry. We have chemical, iron and steel, non-ferrous metal, non-metallic mineral, paper and pulp, and refineries. While the sides of these dots is an indication of the level of excess of the potential of excess heat that is available. Now, we know that most of this industrial excess heat, about 75%, is not recovered. There is a white paper by the Knowledge Center on Organic Ranking Cycle that, let's say, did an estimation. And if we consider to take only the low temperature and medium temperature excess heat that is now not exploited in Europe, and we exploit it by waste it to power, we would produce a potentially around 150 terawatt-hour electric per year. Now, this number, 150 terawatt-hour, is about 5% of the total annual electricity produced in EU 28, is the annual electricity consumption of more than 20 million households, and is responsible for emission of around 45 megaton of equivalent CO2 per year, if you consider the average emission in the EU 28 for power generation. More in the specific, organic ranking cycle, also known as with the acronym ORC, is a competitive technical solution to valorize industrial waste heat and convert it into electricity. I'm not going to explain the general schematic of an organic ranking cycle because I consider that everyone here already know the system. If you want then me to explain it, please write a question and I will do in the Q&A. But here I would like to focus on some rather positive aspect of this technology. In fact, the electricity generated on site by the organic ranking cycle does not cause any additional emission and is dispatchable and reliable. Furthermore, in a context where electrification is becoming more and more important, the electricity produced by the ORC can be used directly on site without further burdening the transmission and distribution grids. And finally, the electricity generated on site by the ORC contribute to the reduction of the European Union dependence on fossil fuel and imported fuel. In this context, the DECAGONE project takes place. DECAGONE, or demonstrator of industrial carbon-free power generation from ORC-based waste heat to energy system, is an horizon project involving a consortium of 16 partners from 10 countries with a duration of 4 years. It started in June 2022 and it will finish in May 2026, and with a budget of around 18 million euro. The ambition of DECAGONE is preparing the ground for industrialization of advanced ORC-based waste heat recovery system, aiming at wider and faster market uptake. Such an ambition is based on 3 pillars. The first pillar is increase in efficiency at the nominal point, the design point of the ORC, but especially in off-design condition and on the overall, on the whole lifetime of the system. The second pillar is the reduction of the total cost of ownership. With DECAGONE, we want to propose an ORC technology with lower capex and especially with lower OPEX. And finally, the third pillar is system replicability. The technology proposed in DECAGONE will be easy replicable in the main energy-intensive industries. We target mainly the steel sector, metal, cement, petrochemical, glass, and oil and gas. Now, a key part of the DECAGONE project is the demonstration at TRL7 on an industrial scale. In the specific, in DECAGONE, we are going to perform the installation, the commissioning, and operation of a 2 megawatt demonstrator plant that will be use the waste heat from the Trinek Zalazarny steel plant in Trinek, Czech Republic, to produce 2 megawatt electric power. Therefore, to summarize in just one sentence, DECAGONE proposes key innovation making organic Rankine cycle system for industrial waste heat recovery more efficient, cost-effective, and flexible. But basically, how we do it? Within DECAGONE, we set 5 objectives that I list in the following. First objective is the development of new component architecture, model, and technologies. Second objective is validating innovative approach using new experimental setup and design capacities. The third objective is demonstrating real-life operation and validating LCA model. The fourth objective is preparing the next commercial generation of ORC derived from the DECAGONE project. And finally, the last objective is promoting benefit of ORC-based waste heat recovery to key stakeholder and broad industrial uptake. In the following, in this webinar today, we will focus on the first 2 objectives. And we will provide you with a first overview of key innovation for DECAGONE ORC. Now, exploiting waste heat from an industry, such for instance, a steel mill, pose multiple challenges that should be taken into account. Without being exhaustive, we can think, for instance, to the fact that exploiting industrial waste heat means that every fluctuation of the industrial production results in a change, in a variation of the heat that is available for the organic ranking cycle. Moreover, we can think to the fact that depending on the process, we can have a different composition of the flue gas with different dust content. And this has an impact on the heat exchanger part. And then we can also consider the fact that installing a system in an existing industrial facility places considerable constraints in terms of available space for this new system. Therefore, to be successful, the DECAGONE project must come up with a technology that should deal with all these challenges. We have therefore worked on the development of a 2 megawatt hermetic turbo generator, innovative heat exchanger for efficient waste heat recovery, thermal storage, active magnetic bearings, and on the nominal point tracking system. Moreover, since we want to optimize the system with some models that we want also to validate and retrofit, we worked on a combined quasi-steady state and dynamical modeling, and on advanced monitoring, control, and data processing. And once that the demonstrator will be in operation, we will perform in operation control and monitoring, and we will validate the modeling, and we perform the retrofit of the component design. Today, DECAGONE is it's almost at the mid-life of the project. 24 to 21 months as already we already work for 21 months, and now I think that for the moment I can thank you for your attention, and I will be available at the end of this presentation of this webinar to answer all questions about DECAGONE project, and I leave you with the technical presentation that will introduce you to the to some of the innovations that we studied in these first 24 months of the DECAGONE project. Thank you.
Thank you, Aldo. Trond, the floor is yours.
Okay, thank you. Yeah, so my name is Trond Andresen. I come from SINTEF Energy Research, which is a research institute in Norway. And today I will talk about some of the aspects and considerations around our heat recovery system for an ORC, and very much specifically for the demonstrator in the DECAGONE project. So before I start, this has been a collaboration with most partners in the project, but what I'm presenting today, I think, is mainly can be accredited to input and contributions from SINTEF, Enertime, and from CEA. So I will not take the glory of all the work here, but I'm happy enough to present it. So I think I'll start to talk about a little bit about what makes the conditions at our demonstration site special, and then I have to select something because we have done a lot of work in the last 2 years. So I will talk mostly about the waste heat recovery heat exchanger and the thermal storage as part of this heat recovery system or subsystem. So first, one can make some questions or reflections about why we are really focused on this demonstrator, and I guess that's also what's really interesting for most of us. But DECAGONE is an as Aldo just said, it's a research and development project for, let's say, the next generation of ORC technology. And on the other hand, it's designing and commissioning and testing a demonstrator for a very particular implementation. So academic and research partners, we have a very interesting role in this project where we are very much clear that and conscious of that we don't have all the answers, but we can maybe offer some different perspective into this development of such a demonstrator. And as we are not really constrained by any product or solution that we are selling, we feel more untethered when we can explore and compare various technology options. And that's one of the things that the research partners in this project have been doing. We have been looking at all the different options and review them in our way. But also, since there is quite a tight schedule in this project, we have to do a lot of things in parallel, which means the more information and realistic behavior about the system and the components we can come up with in the let's say development phase of the project, the more it will help the implementation of the project. So we have also provided some what we have referred to as initial optimized design of the components. And while they don't necessarily are indicative of what solutions will be implemented in the end, this is a way of validating that the performance that we are aiming for can be reached with a design, even when performed by, let's say, researchers. And this is really useful because then we can continue the work with system integration and permitting and site planning and making sure everything fits on the site, and also plan instrumentation and control strategies. So heat recovery, I will talk now a lot about the demonstrator. And as Aldo said, it's to be implemented at the steel plant in the Czech Republic. But that also means that we are very much needing to adapt to an existing process, a live plant and infrastructure that's been built up and evolved for many, many years. And that means that we have space constraints. It means we have very site-specific conditions, for instance, the off-gas we will talk about, and also integration of a system in a brownfield such as this is really complicated. So the heat source is furnace off-gas, and it was documented in the site analysis that the heat content, the thermal power in this off-gas, in this heat source, is very variable. And it's not just the flow rate that's varying, it's also the temperature. So we have two things changing. So while we can see from the site analysis that the average thermal power in our off-gas is more than sufficient to let's say align with our ambition of a power output of the DECAGONE project, the variability is certainly a big issue. We don't want to see this kind of rapid variability in our ORC. So that's a particular challenge. So here I made my own very simplified outline of the whole system, of course aligned around the heat exchangers and thermal storage, which has been my main focus and interest in this project. But in this sketch, we can see that the ORC, the core ORC, quite normal recuperated ORC system is placed here. And then between the ORC and the heat source, we have an indirect heat recovery loop, or if we include all the components in the system, it's what I would call the heat recovery system. And then, as I said, our problem is that this energy in this heat source is quite variable. And we really want to decouple this heat source from the ORC. So if we need to design a heat recovery system that's not only needs to work, let's say, theoretically optimal, but it also has to be implementable and be able to fit in this location. So first, I would say some few words about, let's say, design considerations from the waste heat recovery heat exchanger. And this is what actually sees the highest fluctuation in conditions. But nevertheless, in order to perform a design, what you do first is you, as part of this basic design of the whole system, a system design point also for this heat exchanger was selected, and then we have a set of performance requirements to focus our design around. So that includes duty and it includes temperatures on both sides, but it also means we have a specific pressure drop, a maximum limit on pressure drop that we can that we must observe. And now this design point can be basis for all our various theoretical evaluations, which includes looking at different options for all the heat exchangers, even considering stuff that is not really, it's not feasible for the demonstrator, but it could certainly be possible in future implementations in a different industrial scenario and a different heat source, etc. And that includes stuff like direct versus indirect heat recovery, let's say technology options such as heat pipe, which really lends itself more to a direct heat recovery implementation. So with all that aside, we can start working on how to make the best possible design for this system design point and for each technology we look at. And I think there's many ways of looking at this, but there is really a lot of factors surrounding a practical heat recovery design optimization. You have everything related to performance and operation and site-specific conditions and resistance towards clogging and corrosion and vibration and everything. This is quite something we think about a lot. But for us as researchers, we also have to think a lot about not just what technology is, let's say, thermodynamically suitable, but also what can we find a supplier, or will there be a supplier that will offer such technology? And finally, has this technology been qualified for this similar application? Can we trust it for our demonstrator, basically? Yeah. So with all that in place, we can then start doing design optimizations. And optimizations are really just another word for trade-offs. And so there's no free lunch. But what we are aiming for in our case is what we want to have is the highest possible performance for low cost in a compact package. But we can't, this is not easy to do on a pre-engineering level, and it's very complicated to reliably optimize. So what we can do, which is only linked to physical parameters, is to minimize the weight or the size or the footprint or whatever. But we think that weight of a component is a good dimensionless almost indicator of cost. So then for a demonstrator, we can optimize try to minimize the weight of one certain technology. And for the next slide, I will just show a plain tube bundle in an indirect system, which means the off-gas is here, and then across the off-gas flows the thermal oil in plain tubes with no fins, basically. And then we can produce an optimized design specification of how this heat exchanger should look and whether or not it could meet these performance requirements in a reliable way. And even for such a simple heat exchanger type, there is a lot of design parameters to optimize. As I said, this is inside this shell. There will be this coil of tubes. And then, of course, each tube has a diameter, it has a wall thickness, it has a certain spacing laterally and transversely, and the tubes have a length. These are all continuous variables in optimization. And then we have a lot of configuration options, which are discrete variables, integers, if you will. It's a number of passes, the number of rows, how it is configured and laid out in this. And finally, we have influence from the casing itself. It has some duct plates, support structures and beams and some certain diffuser angle. So the size of the core will then dictate the size of the casing and then the weight of the casing in the end. And as I said, for each of these performance points or design points and performance criteria, we want to minimize the weight of the casing and the support and the core itself together. And we could add on the fluid weight in addition, but in this particular technology, it doesn't. It is relatively minor compared to the steel weight. So We can complete the design such as this that we can propose, but it's really important to understand the influence of these parameters that we have decided upon in this design point, in the performance criteria. And I think one that's really not so easy to relate to, but it has crucial importance, is the gas side pressure drop. So since we have considered that you need to use a booster fan to compensate for any pressure loss on the gas side in our system, that fan work will be detracted from the net power. So naturally, we want to have a very low pressure drop on this gas side. But if we perform such a weight optimization for different budgets in flue gas pressure drop, we can clearly see that it's the weight of the heat exchanger, and then that also very much indicates the overall size of this heat exchanger. And that again translates to cost. So if you want to have a heat exchanger with very little fan work, it means it will be massive and expensive. And at some point, it will probably not fit at the demo site. So this is very much an example of a real trade-off where we end up, we think a good trade-off will probably be in this region somewhere. But there are benefits and trade-offs to such an optimization. And to understand that and to take that into system design is interesting but complicated. Yeah, so then when we have our example design, then we very much need to understand the off-design behavior, because this is the component that will see the highest variation in conditions. So with a fixed design of everything, we can then investigate how the oil temperatures will change with the temperature and flow rate, and how the capacity, the duty of the heat exchanger will change. What kind of outlet gas temperatures will we see that will propagate down the rest of the system, and the pressure drops on the oil and gas sides. Again, I guess it's you fix the design and you do the off-design behavior test, more or less, to see if it's compatible basically with a control strategy and an operational envelope for the system. Yeah, so that brings me over to the next point. We have seen a little bit about basically the design considerations going into this component. Now we are turning on to the next, maybe most exciting component in the system, a clear novel addition in a practical demonstration. And it is the thermal storage that enables such a decoupling of the energy in the heat source and the energy that is supplied to the ORC. And also with this component, there are many considerations. There are so many options. The first is to kind of consider how are you going to integrate a thermal buffering, a thermal storage into your system. I cannot cover everything here, but it was decided to use an indirect loop, luckily, and to place the thermal storage in parallel with the evaporator of the ORC and the wave recovery heat exchanger. And further, there are really a lot of not just technology options, but like families of technologies. You have thermochemical, latent, and sensible heat as a common three families, and each of these has a tree of different options and variations and materials and solutions. But we also need to think a little bit higher TRL for the demonstrator. So this was considered for the general technology integration, but for the demonstrator, we have gone with a dual media thermocline, which is a cylinder, a tank with a solid material where the oil flows around it, and it's the dual media. The oil that flows around it is the thermal oil from the indirect loop. And then from this, we can do a lot of detailed studies that needs to close knowledge gaps or to perfect the design, and then finally understand what kind of capacity do we need to meet the requirements for the demonstrator, and then move on to mechanical design. So the thermal storage capacity, what kind of capacity do we need? Again, it started with many different ways of analyzing the available data from the demo site. You use different filters, different approaches to understand the most critical characteristic that requires the storage capacity in the thermal storage. So in this very principle sketch of it says uptime, but it's more the percent of time we are able to supply the ORC with sufficient heat to maintain consistent and continuous operation. And we found some target area where we cover almost all the scenarios of heat source, so we can maintain operation, and it will be in a few megawatt hours of effective capacity. And now just a few examples of detailed studies that was performed. First, regarding the actual design, you can imagine that it's important for us to maintain a very clear separation between hot zones and cold zones in the storage. As we are charging it and discharging it, this line moves. We want to avoid mixing whenever possible to maintain effective and high temperature storage. So then understanding and designing the inlet flows and outlet flows is really important to avoid mixing. That is such an example of a study. Another one that perhaps is more lesser thought about is in the long term, how does the fluid react with the solid material in such a dual media storage? So here in the labs of SIA, they are performing long-term tests at correct temperatures and pressures, and to see how this both the oil and the material changes over time. And the results are, to me, quite remarkable. It underlines the importance of such tests, let's say, to select the correct combination of materials. Yeah, and all of this kind of culminates into being able to start making the mechanical design of this thermal storage, thinking about not just the thermodynamic performance, but also all mechanical loads, thermal loads, finding a solution for storage material, distribution, instrumentation, control strategies, etc. So it is really a lot of broad range of activities that leads up to the final design of such a component. But it's clearly something we really, really look forward to see in operation. So that brings me up to my summary. I would really argue that the heat recovery is not a component. It is really a subsystem that needs to be handled as such. And the components in the heat recovery subsystem, this is a very, let's say, early rendition of how the system could be implemented at the demo site, but we can see some representation of the thermal storage here and the waste heat recovery heat exchanger here. So they are really big components of the overall system, and also probably a very significant part of the overall cost, but they are crucial for the performance of the system. So that's basically it. This is a very interesting way and to combine takeaways from the theoretical studies performed by a research partner with the feedback that and the solutions that have been proposed from the suppliers, and see how we can kind of make the best possible combination in the end. So thank you.
Thank you very much, Trond. So everyone, if you have any questions, please, again, there's the Q&A session, so don't hesitate if you have any questions. And now we leave the floor to Christopher Schifflechner from TUM. Chris, the floor is yours.
Thanks. Yeah, hi everybody. I hope you can see my screen. And yeah, in the next 10 minutes, I want to give some insights on the ongoing activities regarding innovative cycle designs being carried out in DECAGONE. And so in general, the content of the next minutes is an overview about the ambition and the first results from the work package about the system design, which is coordinated by TUM, but also incorporates a lot of input from other project partners like SINTEF, NTUA, and Enertime. And so within the work package, we want to achieve several things. And as you can see here on the slide, there are mainly two branches. The one is the design of the demonstrator. So identifying the optimal design for the 2 megawatt ORC unit, which will be installed. And of course, this is highly interconnected with the activities on the actual heat exchanger design presented by Trond a few minutes ago. So within the work package, first, we looked into the preliminary design of the demonstrator, which was then the input for the heat exchanger design and optimization. And based on the feedback there and several iteration loops, we are developing at the moment a detailed process flow diagram and P&ID of the demonstrator, as well as the 3D integration of the demonstrator on site. And also with respect to the control strategy of the demonstrator, we are currently identifying the optimal one for the fluctuating heat source conditions. But we are not only looking into the design of the demonstrator, but also want to study and identify and design innovations and improvements for ORC's systems for waste heat recovery in general. And here, on the one hand, we're looking into the application potential of fluid mixtures. We are looking into detailed multi-objective design optimizations, which is then also related to detailed off-design modeling and advanced control strategies for the transient ORC behavior. And so with respect to the general performance and design of the demonstrator, we carried out detailed simulations with respect to study the impact of different plant configurations. And here you see some numbers, not 100% representing the actual demonstrator, but in the same magnitude, which have been also presented by our partner SINTEF at the last ORC conference, where for a selected design point representing the average characteristic at the demonstrator site, we looked into non-recuperative direct evaporation concepts and in general studied the impact of different design choices. And as you can see here in the selected base case, we achieve a net power output of roughly 2 megawatt electric. And so while the neglection of a recuperator would have resulted in a significant drop of the achievable net power output, and at the same time, a system which would consider direct evaporation, so no intermediate, for example, thermal oil loop between the heat source and the ORC, would only result in a small increase of the achievable net power output. And in combination with the strong fluctuations of the heat source and the ambition for a novel thermal energy storage system, which was presented by Trond before, this is then also one of the reasons why this indirect design with the thermal energy storage was chosen for the demonstrator. And another important aspect when it's about the design of an ORC is, of course, the condenser technology, because due to the limited achievable efficiencies, due to the medium temperature heat input, a lot of the heat is rejected at the condenser. So therefore, the design of the condenser is quite crucial with respect to the costs, but also auxiliary power demand for example, driving the fans of an air-cooled condenser. And so next to the air-cooled solution, 3 alternative condensation approaches have been evaluated, mainly with respect to the direct water condensation and, for example, spray-cooled air condensation. And again, start looking at first at the base case. We see that in theory, a direct water cooling system would increase the achievable net power output by around 200 kilowatt, while the spray cooling only has an increase of around 70 kilowatt. And in general, the direct water cooling would have been a measure to increase the power output also for the demonstrator. But of course, it also requires the constant availability of cooling water, which is for the demo site not the case, and therefore an air-cooled condenser was chosen. And what is currently also ongoing by one project partner from the University of Liège is that in-depth studies are carried out for the different condensation technologies, also considering the various climatic conditions across Europe, so to study the effect of the different condenser technologies in different regions in detail. And when it's about the demonstrator and cycle design, of course, also the heat source outlet condition has a certain impact. And there we have a trade-off between maximizing the heat extraction rate from the flue gas and, of course, avoiding local condensation on the waste heat recovery heat exchanger surface. And so therefore, with respect to the required materials and temperature pinch point in the waste heat recovery unit, we studied in detail also the impact of the outlet temperature of the heat source on the achievable net power output. And here we see with the dashed lines, which indicate solutions where the temperature is below the general limit we set to prevent flue gas condensation for standard case, that in general the power output is not very sensitive to the heat source outlet temperatures, and therefore it doesn't make sense to put a lot of effort in solutions which would allow slightly higher cooling down of the flue gas stream, because you would only get a very minor increase of net power output. And as also mentioned by Trond before, when it's about retrofitting a waste heat recovery ORC system in an existing industrial setting, in reality, often space limitations are quite important challenge which needs to be tackled. And so therefore the available space for the ORC, and therefore also the available volume and space for the heat exchanger is limited. And this brings us to the question, how do we want to allocate the available space to the different heat exchangers? And here the partners from SINTEF carried out quite detailed optimization studies where they decided that the share of the area between the different heat exchangers is a design parameter which can be optimized by the simulation model. So therefore it's not fixed about what is the exact pinch point and area of each heat exchanger, but the system is optimizing it for different general stated heat transfer areas in some. So for example, if the system has 10,000 square meters of heat transfer area available, which can be allocated to the different heat exchanger types like the condenser, recuperator, or evaporator. The system is optimizing their allocation. And of course, on the one hand, we see that, as expected, that for higher potential heat transfer area, the net power output can increase. But also the results highlighted that having such a sophisticated optimization routine, which allocates the heat exchange area between the different heat exchangers, can increase the achievable net power output by more than 5%. And so, already concluding my short presentation. So in summary, we looked at the preliminary design of the demonstrator, and also dealt with optimizing the heat transfer area allocation for waste heat recovery ORCs. But also has been carried out so far were detailed studies on the fluid mixtures and their potential, which here wasn't shown due to time constraints, but I can recommend one paper from our partners at CER, which was presented at the ORC conference in September. And so, what are the next steps? We are finalizing the PNID and the 3D model of the demonstrator, and we will carry out detailed off-design and dynamic simulations, as well as thermoeconomic optimization studies. And here, some papers will be presented in the upcoming ECOS 2024 conference. And thanks a lot for your attention. And so I stop sharing. And
many thanks, Christopher. And so now we have Professor Vincent Lemort from University of Liège. Vincent, the floor is yours. Yeah, can you put in full screen? Yes, please, if possible.
Okay, does it work?
It's coming. It's not full screen yet.
Okay, I don't know. It is on my computer, at least.
Maybe it's just me, but I don't think so.
Or is it
Yeah,
okay.
Can you zoom in a little bit and then I guess it's fine.
So is it working like this?
Yeah, yes.
Okay, so I propose we start. So good morning, everybody. So I'm Vincent Lemort from the University of Liège. So myself, I will talk about the performance of our ORC system in of design, and to indicate also some means to improve this performance and also to increase the reliability of our ORC power systems. So you may know that ORC often works in of design regime, and that yields lower performance as expected, which is not very good. And so I would like to understand why, first, what is off design? So what I call off design is some operations, some conditions that are not the one that have been considered for sizing the different components of the ORC systems. So that what I would call also non-nominal conditions. And off designs has some reasons. So the first one is it is due to the variations of the heat source and the heat sink. Time variation could be also variation of the load that is imposed by the expander or the turbine or generator. And typically, so we have to manipulate some variables to adjust the range of operation of the system to bring it in a safer and more reliable zone and most efficient zones. So sometimes we have to play on the speed of the pump. So this is, for instance, what we call the part load operation, where we reduce the speed of the pump. But off design could have other reasons. So it could be due to degradation at different paces. So it could be simply aging of components up to a total failure of the components. But not only the components, might be due also to sensors. And then we have to detect some faults. We have to propose some diagnosis, and potentially also to adapt to implement some predictive maintenance. So this is something I will talk about a little bit later. But there is another reason why the system may operate in off design. So that might be due to a gap between the predictions of the models that have been used for sizing the different components of the ORC and the actual operating conditions. So if we consider even nominal conditions, we could have different pressures, different heat transfer rates, different powers than the one that have been expected. And this is due to some limitations of the models. So the models may not, for instance, take into account correctly the impact of the oil, the impact of the charge. And also some off-design condition may be due to some deviation from the design specification when the ORC is under construction. So I would like to give a few words about the impact of the charge, of lubricating oil. I will talk about sensors, fault detection and diagnosis, and then I will present the ORC lab scale test bench that is under construction at the University of Liège in Belgium. So you know that the performance of an ORC system will depend on the quantity of fluid inside the loop, what we call the charge. And the repartition of the charge among the different components of the system will depend on the operating conditions. And this is what is shown here on the right, from the top to the bottom. If we increase the load on the evaporator by increasing the pumps or reducing the superheat at the turbine inlet, so we are going to have a lower quantity of refrigerant in the evaporator, so a lower subcooling, and so a lower condensing pressure, which is beneficial for the ORC system. So we have to develop some charge-sensitive models. They are useful for minimizing the charge of working fluid, and this is especially important for flammable fluids. We want to limit the quantity of fluid, but also to correctly size the components of the ORC, to correctly predict the performance in of design during design of the system, and also to optimize the controllers. For that, we need, and this is what is very tricky, so we need experimental data for calibrating the heat transfer and the void fraction correlation that are used in the heat exchangers. And so this is during the design. And during the operation, charge-sensitive models are also very useful. They can be used in combination with FDD, so fault detection and diagnosis, to identify some leakage of working fluid, but also to derive what we call active charge management techniques. And this is some techniques, physical techniques that are used to control the quantity of fluid inside the loop and to adapt it in off design in order to, for instance, to minimize the subcooling and so decreasing the condensing pressure. So this is what we saw on the previous slide, to increase the control versatility, to increase the operating map of the system, and also to decrease the response time that could be also beneficial. The second aspect is the oil. So oil has different aspects of different effects. So first, it will impact the performance of the heat exchangers. So it will degrade the heat transfer coefficients. It could increase also the pressure drop through the heat exchangers. It could be deteriorated if there is some hot spots in the evaporator. And there is also a risk of oil trapping in some places of the ORC, and so a bad return of the oil to the turbine. But also very important is the fact that the properties of the mixture of oil and working fluid are not the one of the pure fluid. And this is what is shown here on the right. Even if we have a temperature that is higher than the saturation temperature, so we have some apparent superheat, we still have some working fluid that is not vaporized, but still in liquid phase mixed with the oil. And so the superheat is only apparent. And so this graph is for a given pressure and a given oil circulating ratios through the cycle. And this effect is even more important if the oil circulation ratio is important. In our case, the presence of oil in the system might be due to some leakage that are very difficult to avoid due to dynamic sealings in components of the different machinery. Sensors are very important, so there is a trade-off to be found for the selection of sensors between the cost, the accuracy. For the accuracy, maybe we are not going to use the same accuracy for sensors used for control. What is important is the drift. Then sensors used for calibrating the models of components. It's also very important to keep in mind the accuracy of the sensors at the bottom of the scale, especially for system operating in partnered operation with reduced flow rates, for instance. And some sensors should be characterized by very short response times. For instance, temperature sensors that are used here at the inlet of the turbine, they should react very fast in order to protect the turbine. And then we have installation constraints. The system should be ATEX. We have to cope with pipe diameters and lengths, the direction of the flow. For instance, in the case here on the oil loop, in the case of the thermal storage, during charging and discharging, the flow could be reversed. So we have to use, for instance, current flow meters that could be bidirectionals. And we have also to take into account the flows that could be upward and downward in the selection of some of the sensors. So we saw that degradation forces the system to be of design. Of design means degradation of performance, and so deterioration and decrease of the economical benefit of the ORC. But we know also that if we want to service, to repair, or to maintain the system, there is also a cost, and so there is a trade-off to be found in terms of time when we have to service the system. If we wait until full failure of a component and full reparation, the cost could be very high. So in the project, we design and we implement algorithm for fault detection and diagnosis and method for predictive maintenance before failure occurs. And such method needs to have some models of components that are able to simulate degraded performance. So this is very important. But prior to fault detection and diagnosis, so we have to clean the data. So we have to develop statistical method to define the outliers in the experimental data. Also to increase the quality of the data set using, for instance, what we call data reconciliation methods, where we implement some corrections on the measurements, taking into account the accuracy of sensors, but also meeting the physical constraints like the energy balances of components. So these are some statistical methods we are applying in the project. So all these algorithms allows to have cleaner and more reliable data, to detect faults, to enhance the control, to generate alarms to the operators. And for instance, in terms of control, what I show here is that we have faults that could be on the actuators, on the ORC itself, on the sensors. So first, we are going to use data reconciliation methods to have clean data. And then using FDD techniques, so we can, for instance, transfer some alarms to the human operator that could step back to manual operation of the ORC system, or we can adapt the control of the system in order to bring the ORC module, for instance, in a safer region, maybe less efficient, but safer region until maintenance is applied. And so in the project, so we are investigating different types of faults. It could be clogging of heat exchangers, could be leakages from the system, could be a wearing of turbo generators. but it could also be the sensors themselves. So we could have failures of sensors, total failure, so the sensor is not working anymore, drift or BS in the measurement, and that has to be accounted. So we are constructing a test rig right now in Liège. So the idea is to get more knowledge about the oil and working fluid separation techniques, but also in general some more knowledge about oil working fluid mixture properties, to validate experimentally some charge-sensitive models and also some active charge management techniques, and to validate some fault detection techniques and methodologies, including especially wearing of turbines and leakages of refrigerants. Some very quickly, some specification of the test bench. So we have a heat source from around 10-20 kilowatts. This is an ATEX system. The system must meet ATEX regulation because we are using cyclopentane. And we are not using a real turbine, but we are emulating it with a valve and a heat exchanger, so the superheater here. So we can, with a simulation model, reproduce the exact operating conditions of the turbine at the inlet and the outlet. The test bench is fully instrumented, but what is very important, so we have 3 load cells in order to measure the charge repartition between the major components of the system, the one that accounts for the largest quantity of working fluid. So we're weighting those components. So this is what you can see here for the condenser. It is on the scale, and for the liquid receiver. And so with this test bench, so the goal is to, and these are the innovations we are expecting. The goal is to develop the first charge-sensitive test bench operating with cyclopentane, to our best knowledge, to have more data for validating charge-sensitive models with cyclopentane, and also to fill the gap in the literature about cyclopentane oil miscibility, solubility properties. And last but not least, to investigate some active charge management and fault detection and diagnosis techniques, with the aim at the end to extrapolate those techniques validated at lab scale to large scale systems onto the 2 megawatt scale ORC module. I'd like to thank you for your attention, and I will be there for the Q&A session.
Thank you, Vincent. And now the final speaker of today's webinar is Ole Martola from SpinDrive. Ole, the floor is yours whenever you want.
Yeah, hello everybody. And I will share my presentation.
All good.
Can you see that?
Yes, you can start.
Okay. So next 10 minutes, I will speak about active magnetic bearings, which is also involved in this project. And so I'm Ole Martola, Business Development Director in SpinDrive. And SpinDrive is a designer and manufacturer of customer-specific active magnetic bearing systems. Okay. Okay. Let's go down here. For some reason. Okay, now. Okay, so I'm not going in very much details in AMB technology. I'm just going to show you the overview that everybody understands, just the big picture what AMBs are about. And this is just the general structure of AMB system. And this is kind of very normal setup of active magnetic bearing system. And here we see there's a rotor in the middle, rotating part, and then we have radial bearings on the side. We have 2 radial bearings here, and then we have position sensors, and then we have axial bearings and backup bearings. And the principle of active magnetic bearing is that they are electromagnets, and this rotor is levitating in electromagnetic field without touching any other parts in the system. So it's the rotor is completely like up in the air all the time. And these radial bearings are supporting the radial direction, and the axial bearing is supporting this rotor in axial direction. And so the operation principle is such that these position sensors are reading continuously the rotor's position and like sending this information to the controller. And the controller is kind of the main brains of the system. And based on the information what is received from the sensors, the controller is feeding the electromagnets, which are the radial bearing and the axial bearing. And the controller is, so the purpose of the controller is to keep the rotor in a central position all the time. It's measuring the position like 10,000 times in 1 second. So the rotor is continuous in a central position. And when the sensors are detecting that something is happening, that the rotor is a little bit aside from the central position, it sends the information to the controller, and the controller is sending power to these electromagnets and keeps the rotor in central position. There are also backup bearings in the system, but they are not participating in this rotating operation at all. So they are just for backup. For example, if there's a power loss, or let's say some significant damage in the system, or if you want to turn off the system, so then this rotor is resting on this backup bearings. So that's how any damage is avoided, or any touch is avoided between the rotor and the stator parts. So this is the operation principle, and as the radial bearings are supporting as I mentioned, the rotor in radial position, then axial, the electromagnets in axial bearings are supporting the axial direction. And there's kind of a axial disc in this setup, where the axial disc is between two electromagnets, and that's how that is controlled. Okay, and then what are the AMB technology advantages? So I have here. So AMB system is very tolerant to harsh environments as well. So because there's no need for complex structures, and if there's anything, because there's just the air gap between the rotor and the stator parts, so there's not big problem if there are some small particles in the air, so they doesn't destroy or affect the magnetic field. And also the active magnetic bearings are operational in vacuum environment as well. So as I mentioned, there's no contact at all between the bearing elements, so there's no physical contact, so there's no frictions. There's no component wearing coming out of that, and because there's no touch, the operation is very quiet, and that affects to the maintenance cost. And that was also one of the targets in this project. Active magnetic bearings are completely oil-free, so the benefits there is that if there's any process where oil is a problem. For example, in food processing industry, for example, there can't be any oil in a process. So that is tackled here. And then other point benefit here is that you don't need a lubrication arrangement in a system. So for example, if you have mechanical bearings, so then you have to somehow arrange how the bearings are lubricated. Then since the controller is continuously monitoring the system, it's kind of built-in conditioning monitoring in AMB system. So you can have this predictive maintenance, as actually what Lemort was presenting. He mentioned about these sensors that can be kind of connected to AMB system, and then this easy integration, for example, some other monitoring systems like SCADA. AMB technology is consuming very little. It's energy saving system since there's as mentioned, there's no friction and losses. And if I'm taking an example, for example, let's say one megawatt machine, if you calculate like 3% bearing losses, so that makes already like 30 kilowatt bearing losses. But one AMB system consumes only, let's say, in our system, for example, maximum 500 watt. So it's quite significant difference compared to bearing losses. Then AMB system is kind of dynamic environment. So you have certain like options to adjust the system according to what is happening there. So, for example, if there are some unbalances coming to the rotor, so they can be corrected with the AMB system. And then the last advance that I mentioned here is that so that it's suitable for variable and high-speed operation. So basically, AMBs are not limiting the speed of the machine. So there's no limitations. Before AMB system is a limitation, then there are more like physical limitations in the system. And there's limited start and stop cycles, what is, for example, compared to air bearings. And then the speed variation, there's no effect to what speed you are operating. So you can levitate the machine with 0 speed or then up to top speed. So this is just and in what AMBs in this DECAGONE project, we have there are two spinning parts here. Is this turbine and generator, and both of them are equipped with SpinDrive active magnetic bearings. Some challenges what we are now dealing with is that the temperatures are quite high, but we want to keep the materials what we are using. We want to keep the standard, but at the moment it looks like that it's very much doable. And then there's this working fluid can be something what we must consider in this project. So these are those kind of main challenges what we have in this DECAGONE project. And all those challenges what we have, we can always cover with different material selections. So that's not but it just that is part of this project. Yeah, thank you.
So many thanks, Ole, for your presentation. So this is the end of the presentations. So now we'll go to the Q&A session. So we had 2 questions at the very beginning during the first presentation. So the first question is from Elias Boisard. What is the efficiency of the ORC, megawatt-hour electrical saving, megawatt-hour heat consumed. So Aldo, maybe if you want to answer this question, or any other speaker.
I think I can answer this question.
Okay.
And then if more information is needed, I think that Christopher and Trond and also Vincent can let's say integrate my answer from let's say what we have seen in presentation from Christopher before. Let's say that during this first 21 months of DECAGONE projects, we have, let's say, carried out several test cases on the, let's say, DECAGONE ORC technology. DECAGONE ORC technology means an ORC with, let's say, different kind of cooling system for the air-cooled condenser, or different, let's say, technologies also for the heat recovery part. Therefore, let's say that we had several, I would say, for each test case, we had different results, and we have seen that, for instance, cooling water where is available allows, let's say, to have a huge impact on the production of the ORC, and also on the, let's say, cycle efficiency. On the other hand, for let's say this, let's say, to give you an order of magnitude concerning the, let's say, the study, we can say today, and by the way, we are still working on the detailed engineering and the detailed designing of the organic cranking cycle, and then we should also talk about, let's say, the efficiency, not only at the design point, but even let's say in off-design conditions and on the overall life of the ORC. But we can attain an ORC with a gross efficiency that is higher than 25%. I hope that I answered your question. By the way, there is also a conference paper that we that is let's say a joint work by SINTEF. Trond is one of the authors, and Christopher is from TOM, is another of the authors that we presented last September at the International ORC conference in Sevilla. And actually, this conference paper presents all, let's say, the results that we had in the basic design concerning the nominal point. And as Christopher already said, in the ECOS 2024, we are going to show even some results concerning the off-design operation. I don't know if it's enough as a question or...
Any precisions or yeah, speakers? Okay. And so there was a second question. What is the minimum heat needed for the ORC to be operational?
Again, if you want, I can start, and then Trond or Christopher can answer to the question. Or actually, Trond already answered, let's say, in the presentation concerning the heat exchangers and the thermal energy storage. In this kind of industrial waste heat recovery application, what happens is that the production of the industry production obviously used to fluctuate, and this results in a fluctuation of the available heat for the organic cranking cycle, meaning fluctuation changes in mass flow rate of the off gas and in the temperature sometimes also. Therefore, let's say in these kind of operations that can happen in a steel plant or other, or even in other let's say heat-intensive industries, a thermal energy storage is needed sometimes to decouple the heat coming from the process, from the industrial process, with the heat that is injected in the organic cranking cycle. In the case of the DECAGONE demonstrator that we are going to install in Trinec, the 2 megawatt demonstrator, there will be a large thermal energy storage that is going to avoid, let's say, start and stop of the ORC due, for instance, to the important fluctuation that we can observe on the, let's say, on the heat that is available for the organic cranking cycle.
Any precisions, Trond, Christopher?
Not sure if I answer totally to the question. If
Aldo,
not, yeah.
Would you like to? I think maybe the question was on what is the minimal part load fraction of the system. Would you like to comment on that? Because I don't think I should.
No. Yeah, but let's say that usually the organic cranking cycle can work on, let's say, a range that is going from 30-40% till 100%. But again, if you decouple with the thermal energy storage, actually you can increase this, let's say, the productivity, because even if the thermal load goes beyond this threshold, for instance, you still have the thermal energy storage that provide you with enough, let's say, heat to continue to produce, and maybe to run all over the period where maybe you don't have enough heat to, let's say, to keep the ORC in production. I hope that now it's, let's say, I answered the question.
Thank you, Aldo. So there is no more question in the Q&A chat. If someone else has a question, you can raise your hand, and I will open the mic or the camera. Otherwise, we are done with the questions. Now is the moment to speak if you want. All right, it seems to be clear for everyone. So thank you for participating in this webinar. Now we'll go for the final word, wrap up and conclusion. Aldo, maybe, please.
Yeah, okay. So as you already said, this webinar, let's say the video of this webinar will be available on DECAGONE website, and even on the YouTube channel of DECAGONE. This has been the first webinar, let's say, proposed by DECAGONE, but there will be another webinar that will target industries and, let's say, a broad range of interested stakeholders that will come in the following months. And if you want to be informed about DECAGONE activity, don't, let's say, hesitate to sign up on the DECAGONE newsletter. You can do it on the DECAGONE website. And by the way, you can also follow DECAGONE on social media, so LinkedIn, Twitter, or X, and on YouTube. Thank you for attending this webinar today.
Thank you, everyone. Thank you to the speakers, and we keep you in touch for the next webinar. Thank you, everyone.
Thank you.
Bye-bye.
Bye.
Bye.